Hello there. We will now talk about Chapter 12, Section 3, which deals with linear regression inference in regards to the slope or the true slope of the population least squared regression line. And so we're going to make a confidence interval for the slope and do a hypothesis test for the slope. And let me show you the premise of what's going on here. So we have a linear regression situation in this section. So unlike the previous two sections with chi-squared, it dealt with categorical variables. Now our variables have to be quantitative, okay? And we want to see the relationship between these two variables. And so it's going to, all this, the linear regression stuff that we did in chapter 3, by doing this chapter, we're going to pretty much review all of that. But so what happens in regards to linear regression? Let me remind you. So you've got a explanatory variable, which once again has to be quantitative. It has to have, numbers in essence. And so let's say in this case, and then you have a response variable, which also has to be quantitative. And we want to see how the two are related. So in this case, we want to see how study time is related to a score on a test. And so each of these points represents a student and the amount they studied. So this person apparently didn't study much at all, and they made about a 60. Okay. And so this person studied about 1 hour and made, I don't know, 70 something. Okay. And so this shows the relationship between the study time and the score they made on a test. And so this would be a linear regression sort of situation. And so this was done with 10 students. And so what we did in chapter 3 is we would come up with an equation. And so remember, we would on our so in our calculator, remember to come up with the equation. So I entered this data in list 1 and list 2. So I go stat and edit. And so that is the explanatory variable, the study time on the test. And this is what they scored on the test. Okay. And so if we wanted to come up with an equation on the least squared regression line, we would go stat, we would go test, and we go down to option 8. You remember that? Like that. And so we are working with, so I did the wrong thing. Stat calculate number 8. Stat calculate number 8 right there, linear regression. And so we hit enter. So list 1 and list 2 store regression equation in Y1, and you get to Y1 by going to F4 by hitting alpha trace, which is F4. And so then you hit enter. And so there's the equation of our least squared regression line right there. So we would say Y hat is equal to 70.31, let's say, plus 12.32x. Okay. And where we would define X as this and define Y as that. And so there's our slope and there's our Y-intercept for that line. And all right. And so in this case, and there's our R value, we have a very, very strong R value up in the 0.9s. Anyway, the concept of this chapter is that this was done with one sample. Okay. What if we took another simple random sample of 10 other students and measured their study time and measure their score on a test? Well, we would also probably get a very similar sort of thing, but it's going to, these 10 points are going to differ from these just because of sampling variability. And so let's say here's the line there. We're going to get a similar line there that has probably a similar y-intercept and a similar slope, maybe with this particular line on sample 2. So this was sample 1. This was sample 2. We get another one. And so we get, maybe this one is 68.3 plus 13.12x. Okay. So this would be the A and this would be the B there. And then let's say we took a third sample of size 10, and we would get another line. We would get another A and another B. Okay. And so in other words, these A's and these B's, all right, are in estimates. They are estimates of the population y-intercept and the population slope, that if we did it for the whole population, let's say for every student in this, say our population was every student in this district, and there's like 10,000 students in this district. So in other words, if we looked at all 10,000 students in the whole population and came up with 10,000 points, that would create what is known as a population least squared regression line. And so that would in essence be alpha plus beta times x. Alpha plus beta times x, where alpha is the true population y-intercept and beta is the slope, the true population slope, that if we did it for the whole population. Okay, this is the big number in this chapter that we are trying to estimate and we're trying to test on, is the slope of the population least squared regression line. And so what we're going to do is we're going to take our sample value and we're going to make an interval around it. And then we're going to say we're like 95% confident, or whatever our confidence level is, that beta is in that slope. So we would recognize that this is an estimate for that. And then we'll also do a hypothesis test. We'll hypothesize that our beta is, our null hypothesis is going to be that beta is equal to 0, that there is no relationship between the two variables. No relationship. In other words, the least squared, in other words, the true population line is just going straight across. It's just going straight across. There's no relationship. And so we will test that and we'll come up with a p-value. And if the p-value is low, we reject the null. All right, so that's your little preview of this section. And so let's fill this in. The sample slope is b. It's little b, like that. And it is the estimate. It is the estimate, or the statistic. It is the statistic, maybe we should say, the statistic, which is the estimate, the sample value, that is used to estimate the parameter beta, which is the population least squared. So anytime we get a sample slope, we're saying this is an estimate for beta. And of course, a parameter is a number that describes the whole population. The sample y-intercept is A, and it is the estimate, or the statistic, the sample value that we use to estimate the parameter. Parameter is just a number that describes the whole population, and that is alpha. Now, don't confuse that alpha with our alpha of hypothesis testing, which is, if our p-value is below that, we reject the null. This is a different use of the word Greek letter alpha. And so alpha is the y-intercept in the population least squared regression line. All right, so let's talk about our formulas. All right, so we're going to have a formula that for the confidence interval for the slope. And so you remember every confidence interval follows this basic formula right there. It is statistic plus or minus critical value times the standard error of the statistic. Our statistic here is B. That is what we're using as our estimate, and plus or minus, and it is going to be a t interval. It's going to be a t star times the standard error. So that is our formula that you have to be able to use. You can't just use your calculator for this. You will be given this value. Now, there's sort of this standard error of the slope. In other words, the average, this is the average amount that the slope is going to vary in repeated sampling from its mean. Okay, so, and there's one of the last formulas on our formula sheet. So that's the formula for it. They mark it, as opposed to SE sub B, they mark it as S sub B. And so that's the formula. It's really not hard to find. It's just rather tedious. It's just rather tedious to do. And so using this has never been on the AP Stats exam. And and what they've told us, in essence, to tell you, you're always going to be given this number. You don't have to find it. Okay, so there you go. And so anytime you have t, you have to say, well, which t are you using? In other words, the degrees of freedom, and it's equal to n-2 in this chapter. We in essence have two variables going on in this chapter, so it's going to be n-2, and that identifies our which t distribution we're working with. In other words, that little example we just looked at, it would be 8 degrees of freedom because our sample size was 10. In our formula for our test statistic, remember, okay, so our test statistic, any test statistic has this same basic formula: statistic minus parameter over the standard error of the statistic. Well, our statistic here is B. It is B. Our parameter is going to be 0, okay? That's going to be our null hypothesis value, which we'll talk about, over the standard error, which is our new friend, the standard error of the slope. And you will always be given this value, okay, if you need it. So you don't have to use that formula to find it. And so it's a simple formula. So it ends up being, in essence, B over the standard error of B. And so you have to know that formula. So let's look at our first example here, and this will, like I said, this will review us of a decent amount of stuff that's in chapter 3. By doing this chapter, we will, in essence, review what's in chapter 3, and so that's a very That's a very good thing. And so this is going to be a sort of a complete discussion of linear regression inference. And we need to talk further about what could potentially be on the exam. So you need to make sure, in essence, be looking for that. All right, so this says a manager at a clockmaking factory wishes to model the relationship between the number of workers that show up on a particular day and the number of clocks that are assembled that day at the factory. He randomly selects 9 days, resulting in the data below. So each of these, so it's certainly quantitative data. You cannot do linear regression if you had a categorical variable. This is certainly quantitative, the number of workers, number of clocks made. So when they have 8 workers show up, they made 27 clocks. When they had 20 workers show up, they had made 66 clocks. So you would certainly expect a very strong positive relationship here. So now, and so this would be a chapter three thing. It says create the equation of the least squared regression line, okay, and evaluate the effectiveness of this model by looking at the scatter plot, R value, and residual plot. So that's very much a chapter 3 thing. So let me remind you how we do that. So what we would do is we would enter this data into list 1 and list 2. So you just go to your calculator, you take your calculator and you hit the stat button. So you go stat, and you go edit. And so in list 1, I put all my explanatory variable, which is the number of workers that show up. And in list 2, I put the response variable, the number of clocks made. Okay, and so let's come up with the equation of our least squared regression line. The way you do that, stat, calculate number 8, linear regression A plus BX. You hit enter, list 1 and list 2. Okay, if it didn't, let's pretend it didn't say list 2 there. List 2 is above the 2 button, right? And so you would just hit the second and 2 button to make list 2 go there. So second and 2. All right. Frequency list, just leave it blank. And then store regression equation in Y1, which is in F4. So you hit alpha trace, and that'll put Y1 there. And so arrow down to calculate, and so you hit enter. And so that gives you the equation of your line. So there's our y-intercept and there's our slope. And so that's what I wrote right here. Now, it's very important. Whenever you write an x and a y, you define what they are, either by writing it out, or notice I put x is equal to that and y is equal to that. So it's clear to the reader that you've defined your x and y, but make sure your x and y are defined. So the explanatory is the number of workers, the response is the number of clocks made. So that's how you make the line. Now the R value, this linear regression, this R value, if your R value is not there, by the way, it means your diagnostic isn't turned on, which let me remind you about that. There's the R value. So right there, which is the strength of your linear relationship and direction. So anyway, but to make sure your diagnostics are turned on, if the R value doesn't appear, just go mode and then scroll down to your stats diagnostic should be turned on there. So anyway, stat, calculate, number 8, and then store regression equation in Y1. Remember, an R value, anything above 0.9 or below negative 0.9 is very strong and very strong. So this would be a very strong. If it's in the 0.8s or negative 0.8s, it'd be strong. 0.7 is marginally strong or negative 0.7. Anything below 0.7, or in the 0.6s or that we would, we would call that weak. Now that very much depends on whatever context you're dealing with, and that's important, but that's your rule of thumb. Here, certainly, there is a very strong relationship, okay? And so we would write that down. Now, the scatter plot is just an X and Y graph. You just plot the points with a Cartesian graph here, just 8, 27. You just plot all these points, which I did there, and make sure to label and scale your axes. And then the residual plot, let me remind you how to do that. So your residual plot, with the residuals are how far above and below the line each of your points is. It's in essence turning this line sideways like that to allow you to see any sort of noticeable curve, which we don't want. All right, so by doing the linear regression command, it created the residuals for you. And so they're just in the list menu right above the stat. They're in that menu waiting to be graphed. And so the way you can do your residual plot is go second stat plot, which is y is equal to right there. And so hit enter, and then turn the plot on, and then that enter on that first plot, that's a scatter plot. And then list 1, and if it's probably not going to say residuals there, but to put residuals there, you just go second and stat, which is the list menu, and go down to residuals. And so there we go. Now I'm going to turn off I'm ready to graph by hitting the graph button, but I'm going to turn off my y is equal to. Notice how the equal sign is highlighted there. I don't want to delete this because that is my line. So I'm going to arrow over and hit enter on the equal sign, and it turns it off. And so now I can hit graph and zoom 9. And there's our residual plot right there. That's our residual plot. And I drew the plot there. The key thing is we want it to be nice and randomly scattered, and it is. And so what we would say is we would say, I feel great about this model, about using this model to predict, because of the linear and strong scatter plot, the very strong R value, and the randomly scattered residual plot. That is, and you have to have all three of those things. You have to have all three: a nice linear and strong scatter plot, a strong R value, and a randomly scattered residual plot. All three of those things say that you feel good about using this as a predictor. Okay, that is sort of the main sort of thing in chapter 3. Now, let's go to the chapter 12, section 3 stuff. Create a 95% confidence interval for the true population least squared regression line. We would recognize this is we randomly selected 9 days. If we randomly selected 9 more days, we would get a different set of numbers. It'd be similar to this because we randomly selected, we're not getting biased data, but it's going to vary from this because of sampling variability, and we would get a different y-intercept and slope, okay? And so this B is an estimate of the population value, the population slope, which is the Greek letter beta, that if we did it for every day, the whole population of days. And so since B is estimating that, we are going to use our formula for our interval. Now, anytime you have to create a confidence interval, you have to do the TAME acronym, right? State the type of inference. We got to check our assumptions, otherwise known as our conditions. Then we got to do our mechanics. In other words, we have to make our interval. And then we got to do our ending. We've got to interpret our interval in context, right? Interpret our interval in context. So that's what we're going to do. And so the name of the type of inference is a linear regression t-interval for beta. Okay, that's the name that you have to know. Okay, that's the 12th sort of inference you have to know the name of. So you've only got one more. All right, now the assumptions are a little bit complicated here. Remember our assumptions have been, sin, pretty much, but we adapt that. Well, now we're adding on that the data has to be linear. It's in essence sin plus linear. Your book spells out an acronym called LINER. That is your conditions for linear regression inference. The data has to be linear, and then we have to have independence. Okay, independence, which is the same thing it was before. Our sample size has to be less than 10% of our population size. We have to have normality. Okay, this one's a bit new. We have to have equal variance, which is equal variability. We'll talk about that. We can't have it, in other words, when you look at the residual plot, you can't have it look to where there's different variabilities, like if it's for different values of X. So your residual can't be like really close in line there and really wide here. That would be unequal variance. And so that would be a violation of that. And then lastly, our most important condition, and always a condition for us, is what? Starts with an R, has to be random, or a simple random sample. It's basically sin and make sure the data is linear. All right, and so here we go. All right, and so to check this condition, as shown in number 1, the data is linear. Okay, the data is linear because you look at the scatter plot, there's no noticeable curve. All right, independence. There must be at least 90 days for our little n, our sample size, to be less than 10% of our population size, because our sample size was 9. All right, then we have normality. Now, the way to check for normality is to make sure your residuals themselves don't show any outliers or strong skewness. So what you could do is to make a histogram with your residuals. So what you could do, there's my residual plot, but I need to look at a histogram of the residuals. So if I go second stat plot, hit enter, and go to histogram of, and I want to look at the residuals. So I would go second list, go down to the residuals, put them there, and then go graph, and then zoom 9. And so, so that's how I drew the graph of the residuals. And so the residuals show no outliers or strong skewness, so normality seems reasonable. Equal variance, the residual plot shows roughly equal variability for all values of X. When you look at the residual plot, they're about equally for every value of X from 4 to 20. It's about equal distance from from the line here, from the axis here. And so that would be in essence equal variability. And then lastly, it says the days were randomly selected, so random condition is met. So there you go. Now, having said all of that, anytime that this has basically been on the exam, they go ahead and tell you assume the conditions for inference are met. So you do need to understand that, I would say, but because this is so time consuming, really anytime this has been on the exam, they've said just go ahead and assume the conditions for inference are met. All right, so that is your type of inference, that's your assumptions. And now let's look at making the interval. So to make the interval, this is what you do using your calculator. All right, so what you do to make the interval is you're going to go stat, test, and you scroll all the way down to the bottom. So in this section, right there, so the F and G. So that is going to be what we're doing in a second. That's for the linear regression t-test. Linear regression t-interval is what we're doing right now. So we hit enter on that. We put our data in list 1 and list 2, frequencies 1 or leave it blank. Our confidence level in this case is 95%, I do believe. So yes, 95%, so I'll go 0.95. And then store regression equation, our regression equation goes in Y1. If it didn't say Y1 there, just go alpha trace, which is F4, and put Y1 there and hit calculate. And voila, there is our interval. There is our interval right there. Notice it tells you the degrees of freedom and S, by the way, which could possibly come in handy, but mainly there's the interval. And so that is how you come up with the interval. And then your conclusion with the interval is just like every other conclusion we've had with our intervals, interpreting the interval in context. I'm 95% confident that interval captures the parameter, captures beta, and say what beta is. Beta is the slope of the population regression line in relating, and then say your two variables, relating number of workers and number of clocks at this factory. There you go. All right. So now, then it says this is the next problem. This will deal with the linear regression t-test. Is there convincing evidence of a positive linear relationship between the number of workers and the number of clocks made? Well, there certainly appears to be so. And so perform an appropriate test. This is a linear regression t-test. A linear regression t-test tells us whether or not we have evidence of a relationship between two variables. Okay, so when you're asked to do a test with linear regression, the name is linear regression t-test for beta. All right, your null hypothesis is always going to be that beta is equal to 0. So it's really similar to what we did before. So the null hypothesis is that there's no relationship between the two variables. Because if beta is 0, if the slope is 0, it means the slope is, it means that, like, let's say we graph the data. If the slope is 0, it means the two variables are totally unrelated. Okay, it's just going straight across. In other words, like, let's say if we were talking about the the test setting data and the score on a test, and let's say this is 0 and this is 5, and this is the score on the test. All right, well, according to this data, it doesn't matter how much you study, 0 to 5 hours, you're still going to get the same score on the test. So if the slope is 0, it means no relationship. So our null hypothesis in this section is always going to be beta is equal to 0. In other words, there is no relationship. There is no relationship between our two variables, between the two variables. Okay, that's going to be our null hypothesis. Now, in this case, it asked us, is there evidence of a positive? So we suspect there's a positive relationship, and that's what our alternative is, greater than, because that's what we suspect. But if it just said, is there evidence of a relationship, didn't say one way or the other, you put not equal to there. Where beta is the slope of the population least squared regression line relating the number of workers and the number of clocks at the factory. We've already checked the conditions, thankfully. Now, how do we get these numbers? Well, we use that other command. And so we would say stat test and scroll all the way to the bottom, linear regression t-test, option F, right there. And so this is our last inference. This is our last new concept of the course of AP Stats. So we hit enter on that. And so list 1 and list 2, frequency is 1. The alternative is greater than, store regression equation in Y1. And so, and there it is. There's our t-test statistic and our p-value. And so, which is a very dramatic one. Our p-value is almost 0. Degrees of freedom is the sample size minus 2. Okay. And so this p-value, which is almost 0, is 3.05 times 10 to the negative 6th. All right. This p-value is less than 0.05. So I reject the null. There's convincing evidence that, and then you restate the alternative. That's just like the p-values we've had in the last several chapters for every other test that we've had. Okay. If the p-value is low, you reject the null and say you have convincing evidence that, and then you restate the alternative. So, or in other words, if you wanted to repeat their language, which would be a good idea to do, there does appear to be a positive linear relationship between the number of workers and the number of clocks made. So it'd be good actually to write that down here as well. So, so there you go. That's how you do it. All right. Now, the other thing, now it's never actually happened on the exam that I'm pretty sure that actually to use this command, okay? Linear regression t-test, linear regression t-interval. What they do is they give you, what's happened a lot though, is they give you a computer printout. You have to know how to read the computer printout, okay? So let's do that. So this says, an entomologist wishes to see the relationship between the amount of insecticide in liters that is sprayed in a 30 square yard plot of rainforest and the number of living mosquitoes that are found in the plot. She did this for 12 randomly selected plots in the rainforest. She then created the equation of the least squared regression line. The computer printout of the regression is below. So we definitely have two quantitative variables, okay? And in regards to the amount of insecticide and the number of mosquitoes. So you sort of certainly expect a negative relationship. The more insecticide they use, the less the number of mosquitoes. All right, you have to be able to read a computer printout like this. And let me remind you, all right, coefficient of constant. All right, that is in essence the constant of a linear equation, that is A. So the first number that is in the thing is A. This number that right below it is B. And your X variable, your explanatory variable, is always going to be listed right there below constant. So that is our explanatory variable, the amount of insecticide, okay? And this coefficient of X, that's your slope, that's B. These numbers that are next to A, you will never use those, ever. So cross them out. These numbers next to B are now important, okay? There, guess what that is? That's the standard error of our slope. Okay. In other words, that's the average amount our slope would vary in repeated sampling from its mean. Okay. There's T. Guess what that is? That's our test statistic. And what is P? That's our p-value. Okay. But anyway, there's is the standard error about the line. We talked about that in chapter 3. That is the average amount our predictions will be off. There's our R squared. We'll never use R squared adjusted. Okay. And so reviewing some of the main things in chapter 3. So is, well, and let me go ahead and say this to you. The equation of the line, you weren't asked to do that. The equation of the line would be y hat is equal to 122.3 minus 6.80 times x, okay? Where x is the amount of insecticide and y is the number of mosquitoes. Okay, so that's the equation of the line. You could be asked to make predictions. You could say, hey, if they use 10 liters of insecticide, how many mosquitoes and would you expect? And so you'd plug that in. But anyway, so we're asked to interpret these in context. So what is A? It's the y-intercept. It's what we predict y is going to be when x is 0. So we would say that in context. So we predict that there will be 122.3 mosquitoes in a plot if 0 liters of insecticide are used. Don't round these because you say, well, there can't be 122.3. It has to be an integer. I know that, but don't round them. So this is based on the concept, if we did this many, many times, this is what we expect the average to be. So don't round them. Same with the slope, don't round the slope. What is the slope? All right, here's the most asked about question in linear regression, is to interpret the slope. The slope is this. For every time x goes up 1, the slope is what we expect to happen to y. Okay. In other words, if you look at the line here, and the line would be a negative line in this case, it'd be going down like that. If X goes up by 1, in other words, if we're on the line and we move over 1, what happens to Y? It goes down in this case, in the amount that it goes down. That's what the slope is. Every time you go over 1 from this line, what happens to Y? It goes down, in this case, the slope. And so that is interpreting the slope. The slope is that number. For each increase in 1 liter of insecticide, we predict, and don't say definitely, by the way, say we predict the number of mosquitoes will go down by 6.8. Since it's negative, you say go down. Of course, if it was positive, you'd say go up. All right. So what is S? S is, in essence, it's the standard deviation of the residuals. It is the average amount we predict the predictions will be off by. So so if we plugged in a value for X, we're going to use this much insecticide, and we say, well, we predict there's going to be, this many mosquitoes. So it is the average amount our predictions will be off. Okay. So predicted number of mosquitoes with this model will be off by 14.72 on average. That is what S means. So those are important to know. All right. And so then we've got R squared. R squared, this number, is the percent of the change in Y that can, in essence, be explained by the change in X. You have to memorize that. It's the percent of the change, or in other words, it's the percent of the change in Y, percent of the change in the number of mosquitoes that can be explained by this model. Okay, and so that's what, in essence, I say here. And so R squared is 88.44%. We would, interpreting that value, 88.44% of the change in the number of mosquitoes can be explained by the change in the amount of insecticide. In other words, the other 11.56% is other variables going on. Maybe, the weather, or, what other environmental conditions that can occur. Okay. But the vast majority of the change in the number of mosquitoes in this case is related to the insecticide. Okay. All right. So now, let's do the chapter 12, section 3 stuff. Create a 99% confidence interval for beta, the slope of the population, least squared regression line. Assume the conditions for inference are met. That's nice. Okay, because we don't have to do the liner. So the name, once again, this is a linear regression T interval for beta. There is our equation. Okay, and so these numbers. So let me remind you. So our formula, as we talked about, is B plus or minus T star times the standard error, and our degrees of freedom is equal to N minus 2. Okay, so you get B off of the table. Okay, so you get B off of the table, and then that number, like I said, the standard error will always be given to you. That is the standard error of the slope. That is SE sub B right there. So that's big. And there is T, that's our test statistic, and p-value for our test. But this is what we need here. And so we have, it's B plus or minus T star times the standard error of the slope. Degrees of freedom is sample size minus 2, so it's 10 in this case. All right, so there's the standard error slope. How do we find T star? All right, so the way you find T star is this, is you could use your table in essence, but I'm gonna use this. So we have, this is a 99% confidence interval. Yeah, it asks for 99% confidence. And so what that is in essence meaning is my T distribution with degrees of freedom is equal to 10. 99% of our distribution is taken up by the interval. That means 1% is on the outside, and half of 1% is on each tail. So this is 0.5 of 1%. This is 0.5 of 1%. The critical value is this guy right here. And so I'm going to use inverse T to find that, 0.005, right? And then degrees of freedom is equal to 10. And so that's what I'll do. And so I will say second distribution, inverse T of 0.005, degrees of freedom is equal to 10. And so there it is. And I make it positive. It's plus or minus in the equation anyway, but about 3.169. And so there you go. And so that's how I get that. So you multiply that times that to get your margin of error right there. And there's our interval. And then anytime you get an interval, you just say you're 99% confident that interval captures the parameter. In this case, beta, which is the slope of the population least squared regression line relating the amount of insecticide and the number of mosquitoes. Okay. And then lastly, we have our linear, do the data provide convincing evidence of a negative linear relationship between the amount of insecticide and the number of mosquitoes? Perform a test. So there's the name of our test, linear regression t-test. The null hypothesis is that there is no relationship. And a lot of times you'll see it written in words, but is in essence that beta 0, there is no relationship, or there's no association between our two variables, the amount of insecticide and the number of mosquitoes. Okay. The alternative in this case, that there is a negative relationship in this case. Okay. And so there's defining beta. All right. So how do our t now, by the way, so on this one, your t-test statistic is given to you. It's that. Okay. But the way that is found, our little formula is B over the standard error of B. It's just that over that. So that over that. So it would be, and that has happened on the exam before, where they give you those two numbers and they don't give you these two numbers. Okay, they don't give you those two numbers. And so you'd have to say that over that to get t, and then use your t to find your p-value. But in this case, and this is what has happened most of the time, they give you t and the p-value. And so your t is that, your degrees of freedom sample size -2. So your p-value is, they listed at 0. It rounded to 0.00. It's really close to 0. It's approximately 0. And so you would say this p-value is below 0.05. So I reject the null. There's convincing evidence that, and then you restate the alternative, which is in essence the way they worded it here. Is there, evidence of a negative linear relationship between the two variables? And so I went ahead and restated, there does appear to be a negative linear relationship between the amount of money, or the amount of insecticide, and the number of mosquitoes. That's it. That's section 12.3. Make sure to be paying attention about what you're actually going to be tested on. This is sort of a complete, very quick discussion of everything there. And we will be talking, on the review worksheet specifically about what you're going to be tested on, and about, specifically what has ever been on the AP Stats exam in regards to this. But thanks for paying attention. And that is all of the new material of AP Stats. And if you have any questions, please let me know. Hope you have a fantastic day.